Hello everyone, thank you for watching our video. My name is Hiroyasu Akada. This work is done mainly by KAUST. Today, I'm going to talk about our work, Self-Supervised Learning of Domain Invariant Features for Depth Estimation. In this work, we are going to solve unsupervised synthetic to real domain adaptation for single image depth estimation problem. In this problem setting, many depth estimation methods try to effectively utilize labeled synthetic dataset as a source domain and unlabeled real-world dataset as a target domain for training. During test time, they aim at estimating an accurate depth map given a real-world RGB image as an input. Encoder-Decoder architecture is an essential block for depth estimation. For generalization in the target real-world domain, previous works have demonstrated that better initialization of the encoder plays an important role. More specifically, pre-training on the real-world data, such as ImageNet, can improve generalization performance in the real-world domain. However, the initialization of the decoder is less explored. Therefore, we propose a novel technique for decoder initialization. In this work, we introduced a novel self-supervised representation learning stage as a pre-training method of the decoder. In our SSRL stage, we used bidirectional image translator CycleGAN and Siamese network so that the decoder can extract domain invariant features. First of all, we use CycleGAN to translate images between synthetic and real-world domains. Here, IS and IT denote synthetic and real-world images respectively. Also, IS2T and IT2S denote their translated versions. We utilize these four types of data to train our weight share depth estimator in our Siamese network. Here, the encoder is already pre-trained on ImageNet, and only the decoder is trainable. From the four types of images I, we obtain four types of feature maps M. Next, we forward all of the feature maps M to weight-shared MLP-based projector, yielding features P. Then we further use MLP-based predictor in either side of the framework to obtain predicted features Z. As a loss function of our Siamese network, we compute pixel-wise negative cosine similarity between features P and Z. In the other side of the predictor, we apply stop gradient operation. In this way, the depth estimator can learn domain invariant features between synthetic and real-world domains. After the pre-training in the proposed SSRL stage, we fine-tune the depth estimator using four types of images I. For the label types of images IS and IS2T, we use synthetic depth maps as a ground truth. For the unlabeled types of images IT and IT2S, we adopt previously proposed cross-domain consistency loss based on the assumption that their predicted depth maps should be the same. We conducted several experiments. In our first experiment, we used virtual KITTI and KITTI as a training dataset. For the testing dataset, we used KITTI. We show the result in the table 1. Unsupervised domain adaptation methods are marked in gray. For a fair comparison, we use the same encoder pre-trained on ImageNet in previous method. The result shows that our approach boosts the performance in all metrics. We also evaluate our method on Make3D dataset. In this experiment, we didn't retrain method on Make3D. Again, our method outperforms all previous methods in all metrics. We also show the qualitative result on KITTI. Compared to previous method, our method can handle brighter reflections and complex structures well. In conclusion, we tackled the problem of unsupervised synthetic to real domain adaptation for depth estimation. We propose a novel framework that enables an encoder-decoder architecture to learn domain invariant representations. We devised a pre-training strategy for the decoder using self-supervised learning. Our method generalizes well in the real-world domain. Thank you.